Oh, no, it's not that one. That's all right. So let's talk about probability, which we've already kind of talked about a little bit, but we should be a little bit more formal. We're talking about so Co-17C. Today is December 2nd. By the way, for those of you that just came in, look, the screen. There's not the green circle of death. So excellent for the last couple of days of class here. Let's talk. Let's do an example, and then we'll kind of talk through some things. So, um, let's say we flip a fair coin. It's flipped 4 times. We're going to start by first listing the sample space. So the sample space, often denoted with the Greek letter omega, is the list of all the things that can happen, essentially, all the possible outcomes. So it's usually a good idea when you do this to be systematic about it. So I'm going to start listing the sample spaces by kind of thinking about the number of heads I get. So for example, we could get 4 heads, which would be heads on the first, second, third, and fourth flip. We could get less. We could get 3 heads. Like the first 3 flips are heads and the last one is tails. Or maybe the first 2 are heads and then the tails and then the heads, or then heads, tails, heads, heads, or then tails, heads, heads, heads. Even though it's the same number of heads, it's a different outcome because the order in which we flip things is different. And then we could have 2 heads, which could be heads, heads, tails, tails, or heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, or tails, tails, heads, heads. One head should not be hard to figure out because it's the same as one tail. We're just interchanging the heads and tails. So it's going to be tails, 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 head, or tails, tails, heads, tails, or tails, heads, tails, tails, or heads, tails, tails, tails. And finally, 0 heads, that's going to be all tails. So how many items or outcomes are in our sample space? Well, let's see, 1 plus 4 plus 6 plus 4 plus 1, looks like there's 16. So the size or the number of elements in the sample space, one way to think about this is what we've been doing before is just counting all the possibilities. So for the first flip, how many possible outcomes were there? This many, right? 2. So there's 2 possible outcomes for the first flip, times 2 outcomes for the second flip, times 2 outcomes for the third flip, times 2 outcomes for the fourth flip. Oh, look, 16, the number of total outcomes we found. So if we weren't asked to list the sample space, we just count the number of items in the sample space, we could say, okay, yeah, there's 16 possible things that can happen. I'll also point out, because I do think it's worthwhile here, these numbers, 1, 4, 6, 4, and 1, shouldn't be terribly surprising. The number of ways of getting 4 heads is 4 choose 4. Out of 4 coins we flipped, we chose 4 of them to be heads, and that's equal to 1. And 3 heads, that's 4 choose 3, which ends up being exactly equal to 4. And for 2 heads, that is 4 choose 2, which is 4 factorial over 2 factorial times 2 factorial, which is 6. So these numbers are exactly coming from, oh yeah, we're just picking how many ways you can kind of pick the 3 spaces or the 2 spaces or the 1 space or the 0 spaces that have to have those heads. It also, I think this is a good kind of example to kind of really show you, oh yeah, If I want to know the number of ways you can pick four heads, or sorry, zero heads from four coins, well, there's exactly one way of picking zero heads, where you get all tails. I feel like that's kind of a better example than picking like no fingers, but same kind of idea. So now let's talk about some probabilities. So B, let's let A be the event of flipping exactly two heads. What is the probability of A? Probability of event A happening. Well, here's how we write this. Really, this question isn't about answering the mathematical question. It's about the notation. So the probability of event A is just like we said last time. I know I said this before. The number of ways A can happen divided by the number of ways anything can happen. And that's very generally true. If you're trying to find the probability of something happening, you count up all the ways it can happen, you divide that by all the ways anything can happen, and that's your likelihood or probability of that happening. So that's going to be 6 out of 16, which I would reduce to 3/8. For the same reason, it's why the probability of getting a head or a tail is 1/2, right? Probability of getting a head is 1/2 because there's one way that happens out of two possible total outcomes. Assuming again, so there are some assumptions made, right? Like when you're flipping a coin, there is an assumption made that there's an equally likelihood of getting a head or a tail. Or like when you're rolling a die, a 6-sided die, there's an equal likelihood of getting any one of the six outcomes. Those things aren't always true, right? There is such a thing as weighted dice, and there are some unfair coins throughout history, but notwithstanding, we assume it's fair unless we're told otherwise. Okay. So what if I wanted to find, let's say B is the event of flipping at least three heads. So the probability of B, and this is where we start to see like throw notation out there that we don't really define well. Like I'm going to write the probability of B is the probability of flipping three heads plus the probability of flipping four heads. Right? There's no overlap there. You can't flip three heads and four heads at the same time. It's either one or the other. So we're kind of breaking this down into all the constituent pieces. The probability of three heads, well, that's going to be the number of ways of getting three heads, which was 4, divided by the number of ways anything can happen, which was 16. And probability of getting four heads was exactly one way out of 16 total ways. So the probability of getting at least three heads is 5 out of 16. So what's the probability? I'm sorry, here I'm getting ahead of myself. Well, let C equal the event of flipping at least one head. What's the probability of C? Well, we don't have to be quite so coy about it. Like we could say it's, the probability of one head plus the probability of two heads plus the probability of three heads plus the probability of four heads. But we could also just say, yeah, I know it's going to be those things. So it's going to be there's 4 ways of getting one head plus 6 ways of getting two heads plus 4 ways of getting three heads plus one way of getting four heads. Each of those out of 16. So that's going to be a total of 15 out of 16. I probably could have done this doing less work. I probably could have instead said, hey, the probability of getting at least one head. So the way I might actually write this, right, instead of writing P of C, I might say the probability that the number of heads is greater than or equal to 1, right? I might just use that notation because it feels natural. Well, if I add that to the probability of the number of heads being less than 1, those are all the possibilities, right? Either you have less than one head or bigger than or equal to one head. By the way, the probability of getting less than one head is really the probability of getting 0 heads. Right? That's the only way you can get less than one head is 0 heads. And a lot of times, right, specifically where we're counting things and it has to be like an exact positive integer number, or not, I should say non-negative integer number, right? Less than 1 means less than or equal to 0, or bigger than 2 means bigger than or equal to 3, because we are going up to the next integer. So here, this should total 100% or 1. And so if I want to find this here, I could say, oh, well, the probability that the number of heads is bigger than or equal to 1 is equal to 1 minus the probability that the number of heads is equal to 0. And that's, in my opinion, a little bit less work. Probability of getting 0 heads is 1 out of 16. And 1 minus 1/16 is 15/16. I know I've said this before. I know I've said this before, but I'll say it again. This idea of using the complement, right? Counting up all the stuff you don't want and then subtracting it from everything to get what you do want is often used, and sometimes, actually not more than often, pretty easy comparatively. These ones not so bad, but like when your numbers get bigger or the probabilities are less, like they're not just 1/2, like if it's 1/3 or something like that, then it gets a little bit uglier, and using this idea really is convenient. Also, if you have questions, don't hesitate to ask them. Let's see here. Yeah, we should get the conditional probability today too. So let me try not to go quite so quickly here. All right, let's look at a whole nother example. Let's say we're going to roll a 6-sided die. And we're going to look at the following. So we're going to say that A is the event that an even number is rolled, and B is the event that a multiple of 3 is rolled. We could write these out. So we could say that A is the set consisting of the results 2, 4, and 6, and B is the set consisting of the results 3 and 6. Sometimes, not always, sometimes it might be convenient to illustrate this with a Venn diagram. So let's draw a Venn diagram illustrating the situation. So typically when we draw a Venn diagram, we kind of draw a big rectangle representing kind of everything that can happen. So anything that can happen should be in this rectangle. And then we draw circles representing the different events. So there's A, yeah. And since A and B have something in common, we should draw them with some overlap, right? If they didn't have anything in common, we would draw them so that they didn't overlap. And here's B. So in the overlap, we have 6. So 6 is common to both A and B. And then we also have 3 in B, but not in A. And we have 2 and 4 that are in A and not in B. And then outside of A or B, we still have the 1 and 5. So those are all 6 possible outcomes. You can roll a 1, 2, 3, 4, 5, or 6. And each of those probabilities is equally likely. Right? The probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6, all the way to the probability of rolling a 6 is 1/6. Again, notice how I didn't like write notation for this. I didn't say let 1 be the event of rolling a 1. We're just using kind of some common sense notation here. Right? Everybody knows what I mean when I write this. The probability I roll a 1 is 1/6. In this context, right? If it was a different problem, it'd be something else. Sure. I know I said it before, but I will say it one more time. I didn't really explicitly say it. It's worth observing that if you look at the probabilities of all the events that can happen, what should that add up to? Right, exactly. 1, right? Everything that can happen, the probability of that should add up to 100% or 1. So if you've written all the probabilities and you're like, those don't seem to add up to 1, double check. So what's the probability that A happens? Well, the probability of getting a 2, a 4, or a 6, that's going to be the probability of a 2 plus the probability of a 4 plus the probability. That looks like it's going to be a 6 plus a 6 plus a 6, which is 3/6, which is 1/2. How many of you like to play board games? It's okay if you don't. It's okay if it's the answer no. So you know how in board game you often might roll a die to see who goes first, and you might both roll and like you might tie. Well, another way to start a board game, which always has a determined outcome when you roll the dice, and it's an equal probability, is to have one person roll any number of dice, and the other person can call odd or even. And there's a 50% chance the sum will be odd, there's a 50% chance the sum will be even, regardless of the number of dice. It's kind of interesting. But it's definitely true here, right? The probability of getting an even result is a half. The probability of getting an odd result, which I know is not on, well, we can say the probability of a complement, everything that's not an A, the probability of getting a 1, a 3, or a 5 is also 3, 6, which is 1/2. But it is interesting that it's true for any number of dice. If you roll 2 dice, it's equally probable that the sum will be even and the sum will be odd. Kind of neat. True for 3, 5, 7, 12, however many dice you want to roll. Obviously, you don't want to roll that many dice, but okay. So, what else do we want to talk about? Oh yeah, let's see. What's the probability of B here? Probability of B is, well, not surprisingly, there's 2 things in B, so it's going to be 2 out of 6, which is 1/3. But really, we're talking about this, so we talk about 2 other things. We want to talk about the intersection. So the intersection or the overlap is written like this: A intersect B. And it's everything that's common to both A and B. So in this case, the only thing that's common to A and B is 6. So it's the probability of rolling a 6, which is just 1/6. And then there's also, so this is the intersection, or as I often say, the overlap. There's also the probability of A union B, which is much easier to remember because the symbol looks like a U and union starts with U. So that's the union. And that's everything that's in A or in B, or the overlap. So looking at what we've got here, it's the probability of rolling a 2, a 3, a 4, or a 6, which is going to be 4, 6. But there's also a formula for it. Check this out. It's everything in A plus everything in B, or the probability of B. But if you look at A and B, if I count up the probability of A, that's 3/6. The probability of B, that's 2/6. But I've counted the thing in the middle twice. So I don't want that. I don't want to double count anything. I'm going to subtract off one of those double countings. So to find the probability of A union B, one formula for that is it's the probability of A plus the probability of B minus the probability of the intersection of A and B to undo that overcounting. And that would be 3/6 plus 2/6 minus the 1/6, which is going to be 4/6, which reduces to 2/3. So, a couple other things to say here. What's the probability of rolling an even number or a 5? So in other words, what's the probability of either event A happening or rolling a 5? Something else I should say about while we're here. When you say the word or in math or statistics, we usually associate that with a union. So A or B means A union B. We can be in A or in B or both. And actually, we should take a minute here to talk more about this. So when we say the word or in math, it's different than in language, right? This is like the typical example. If you go to a restaurant, they ask if you want soup or salad. You don't get both, right? You get one or the other. That's called an exclusive or. Exclusively soup or salad, not both. That is not what or means in math, unless someone says so. If someone says or in math and they don't say anything else, they mean something from column A or column B or both. Both is a perfectly acceptable result. So when I say in the previous example, I want something that happened in A or B, rolling a 2, a 4, a 3, or a 6 is a totally legit result. That's why we counted all 4 of those, and the probability of A or B happening was 4 out of 6. There's 4 things in A or B, or both. Here, if I want to find the probability of something in A or rolling a 5 happens, well, same idea. It's the probability of A happening plus the probability of 5 happening minus the probability of their intersection. But in this case, their intersection is empty, right? A consisting of 2, 4, and 6, and 5 being not in there, those are disjoint or mutually exclusive. So here, A intersect 5 is what's called the empty set, also written as the Greek letter phi. And the probability of A intersect 5, well, the probability of getting something in an empty set is 0. And I should say here that event A and event rolling a 5 are called mutually exclusive, also known as disjoint. So here, this probability is just going to be the probability of A, which is 3 out of 6, plus the probability of 5, which is 1 out of 6, which ends up being 4 out of 6, which is 2 out of 3. Yeah. I'm trying to think if there's more I want to say about that. I think so. Mutually exclusive. Not to be confused with the idea of being independent, which we'll talk about when we get there. But they are different things, very different. So, just to recap, A intersect B is read as A intersect B and is all elements common to A and B. So the overlap. And when I think about the intersection, I think of the word and. I want to find the things that are both in A and in B. Whereas A union B is read A union B and is all elements in either A or B. Or both. But you don't really need to say the both part, right? Because if you're in A or you're in B, then we're also looking at the place that's in the middle. But it's still good to say they are both. And this is sorry. And so here I think of the word or. Here I think of the word and. So A or B is the union, A and B is the intersection. And one more thing just to make sure it's clear. A and B. I know I wrote this. I'm gonna write it down. You don't probably not write this down, but if you did already, are disjoint or mutually exclusive if there's no overlap. If their intersection is the empty set, or the probability of their intersection is 0. I'll point out in math, this is why it's a bad idea to write your zeros like that, because 0 with a slash through it actually has a totally different meaning. It really means the set containing nothing, whereas 0 is the number 0. So I would encourage you not to write your zeros like this if you write them that way, but probably too late because you probably already write them that way and you're used to it if you write them that way. Okay, so moving on. Back to some playing cards. Has your instructor talked about playing cards? Okay, good. So make sure I'm not using examples that are totally like not something you're going to talk about. But if you are, great. That means they're in play. So let's look at this example. And this is number what? 2, 3, I don't know. A card, a single card, I think, is chosen from a standard deck of 52 cards. Find the probability that the card is, in this first question, an ace or a face. So what do we say? What do we mean when we say a face? We mean a jack, queen, or king, right? Those are your face cards because if you look at the cards, they have faces on them. So let's see. Well, this is going to be faces are the jacks, queens, and kings. Aces are the aces. How many such cards are there? Right, there's 16. And I don't feel like so to me, like this question is kind of written as a union. I feel like it's a kind of overkill. I'm going to do it that way still, but so here if I'm thinking of the ace as say event A and the face as event B, and I have an or here, that means I find the probability of A or B or A union B. It's going to be the probability of A plus the probability of B minus the probability of the intersection. The probability of getting ace is 4 out of 52. The probability of getting a face is 12 out of 52. And the probability of getting a card that's an ace and a face is 0, because there are 0 such cards that are aces and faces, right? You can't have a card that's both an ace and a face card. So this is just 16 over 52, which feels not really, well, no, it is kind of worth reducing this fraction. 4 out of 13. Which kind of makes sense if you think about it because you're talking about what's the probability of getting any one of these 4 ranks, jack, queen, king, king, or jack, queen, king, or ace out of the total of 13 ranks. Oh, 4 out of 13. So sometimes if you think about the problem from a different approach, you might be able to, I don't know, I feel like I wouldn't approach it that way. I could still kind of think about all the cards, but it's nice to kind of see that there is a different light to picture this in. Okay, let's make it more interesting though. What if we said we wanted to find the probability of getting a diamond or a jack? Well, now we do need to be a little bit more careful. So again, if we call getting a diamond event A and getting a jack event B, well, then the probability of A union B, although honestly, I'd probably call them like event D and event J because like the things start with D and J, but whatever. Probability of getting A union B, again, I'm just tossing this formula at it. Probability of A plus the probability of B minus the probability of the intersection. All right, how many diamonds are there? Right, everyone's favorite lucky number. 13 out of 52. How many jacks are there? 4. How many cards are there, both a diamond and a jack? 1, the jack of diamonds. I remember if the jack of diamonds is the suicide jack or the one-eyed jack. No, that's the suicide king. Sorry, never mind. There's a couple one-eyed jacks. Anyway, it doesn't matter. So no one's going to ask you about one-eyed jacks or one-eyed kings because that's if you're playing poker, not if you're looking at probabilities. So let's see. Coincidentally, and it is a coincidence here, this also happens to be 16 out of 52, which is 4 out of 13. But for very different reasons. I mean, I guess not really for different reasons. The reasons are the same. There are 16 cards in the deck that meet the criteria. There are 16 cards that are jack, queen, king, or ace. There's also 16 cards that happen to be a diamond or a jack. The 13 diamonds plus the 3 jacks that aren't diamonds. Okay, here's one that's going to feel kind of silly, but sometimes it's good to think about silly things. What's the probability of getting a red card or a spade? Well, let's do what I really want to do. Let's say the probability of getting a red card is R, probably getting a spade is S. The probability of R union S is going to be the probability of R plus the probability of S minus the probability of the intersection. So, what's the probability of getting a red card? How many red cards are there? Or not how many red cards are what's the I mean, if we just think about it, half the deck is red cards. The probability of getting a red card is 1/2. Yes, you can start by saying it's 26 out of 52. 26 red cards out of 52 cards. And the probability of getting a spade is 13 out of 52. But spades are black, as are clubs. Diamonds and hearts are red. So the probability of a red card and a spade is again, 0. Those two things are mutually exclusive. So we end up with 39 out of 52, or 3/4 of the entire deck. In some like online poker things, they have like other colors for the cards. Like they use like I think like red and green and black and red and green and black and blue, just so that so like people with color issues can differentiate between them easily. Makes sense, I guess. All right, so moving on to the real kind of probabilities of cards of poker hands. Not these, sorry, it's five. This is what numbers. You think I'd be able to keep track of my numbers a little better? 4. So typical situation, we're dealing 5-card hands. So dealing 5 cards from a standard deck. Again, if we didn't say the standard deck part, we would still assume that, right? If you're kind of set in one of these situations where you're flipping a coin or rolling a die or dealing cards from decks, we're assuming the usual standard situation unless otherwise is told to us. So I feel like we did some of these before. Whatever. Yeah, we did do some of these before. Interesting. Oh, no, we kind of talked about the numbers before, not the probabilities. Okay, sure. So question A, what's the probability that all 5 cards are clubs? Now we're back in the land of using the choose function. So again, it's going to be, if we call the event getting all 5 cards of clubs, if we call that event A, it's going to be the probability of A is going to be the number of ways of getting all 5 cards being clubs divided by the number of ways you can get anything, or essentially the size of our sample space. Okay, well, there's 13 clubs. We want to choose 5 of them. So there's exactly 13 choose 5 ways of picking 5 clubs. On the bottom, well, this is pretty standard, so you should get used to seeing this number, or I should say this expression for this number. 52 cards in the deck, we're going to choose any 5 of them. So there's 52 choose 5 different possible poker hands, right? Where you look at all the cards individually, or 52 choose 5 different ways of getting any 5 cards. Okay. Sorry, my wife is texting me something. I was making sure it's not important. Okay. She knows I'm teaching right now. All right. So, or she should know I'm teaching right now. She's got my schedule. Let's see. On the other hand, what if we were asking about the probability that all 5 cards are just the same suit? Well, it's essentially what we just calculated, but there's 4 different ways you can do it. So here's one way to think about it, just multiplying it by 4, but I kind of want to be more systematic. So it's going to be, let's say we call this event B. The probability of event B is going to be the number of ways you can get all 5 cards to be the same suit. But we didn't say which suit. So last time there was no choice between the 4 suits. This time there is. So first we're going to say, well, there's 4 choose 1 ways of picking your suit. And then after your suit is chosen, there's 13 choose 5 ways of picking the 5 cards of that same suit. Our denominator is almost always the same for these problems. 52 choose 5. So 4 times as big as our previous answer. There's 4 times as many ways of getting all cards being the same suit versus just 5 of them being the same suit. Just all five of them being clubs. Now you might notice I'm avoiding using the word flush. You might not notice actually. The reason I'm avoiding that word though is because if I said the word flush, then we have to, like last time, exclude the straight flushes, right? Because specifically when we're talking about poker, if you say you get this particular hand, you have to eliminate any hand that might be accidentally be better than that you're accidentally counting. So, but we're not going to worry about that. That's why I just want to point out that's why we're not thinking about that here. So, Oh, sure. Yes, this is a good question here. So here's C. What's the probability that at least one of the five cards is a heart? Okay, well, here's one way to do it. We should just do it the smart way. No, we should not. We should do it. So you might not want to write this next part down because this is not the best way to do it. But here's one way to do it. So we want at least one heart. It's going to be the probability of one heart and four not, plus the probability of two hearts and three not, plus the probability of three hearts and two not, plus the probability of four hearts and one not. Oh my goodness. Plus the probability of five hearts. This, which is not, I mean, okay, it's just some writing, right? Probably of one heart. Well, how many hearts are there? 13. We're going to choose one of them. And then how many not hearts are there? How many not hearts are there? Or how would you calculate it? 52 minus 13, 39. There's 39 cards that aren't hearts, right? 3 times 13. And then of those 39 not hearts, we want to choose four of them. Over 52, choose five. And then same kind of deal for the rest of this. This is going to be 13 choose 2 times 39 choose 3 over the same thing, 52 choose 5, and so on. 13 choose 3 times 39 choose 2, 52 choose 5, plus 13 choose 4. Oh my goodness, times that's a 39 choose 1. That should be a 1 there. Sorry, it's a little hard to read. Over the same denominator. And finally, 13 choose 5. You don't really need the 39 choose 0 because that's going to equal 1 over 52 choose 5. Or you could do this the smart way. Okay, or it's going to be 1 minus the probability of 0 hearts. And the probability of 0 hearts is going to be, well, there's 39 cards that aren't hearts, so it's going to be 39 choose 5 divided by 52 choose 5. And if you have the time, you can check that these are the same. They are the same. I don't want to calculate them because it's a lot of calculator work, but that should be exactly the same probability. So why don't you all try answering this next one in the same sort of easier way? What's the probability that at least two of the cards are hearts? And again, I would encourage you to think of it as 1 minus the stuff you don't want. So if we want at least two of the cards to be hearts, we don't want 0 hearts and we don't want 1 heart. So we're trying to find 1 minus the probability of 0 hearts plus the probability of 1 heart, which is going to be 1 minus that thing we had up there, 39 choose 5 or 52 choose 5. And then I guess I put this in brackets here, plus getting exactly 1 heart is that one right there. It's 13 choose 1 times 39 choose 4 over 52 choose 5. And you probably write that as one fraction. I'm just writing it like that because I don't know. It makes sense to me that way. Okay, one more of these, and then we'll start talking about conditional probability. So here's a question that is kind of interesting, I think. Hmm. So let's look at this example here. This is sure five. So if there are 5 people in the room, find the probability that 2 people have the same birthday. So this is another example of it being much easier to count up what we don't want versus what we do want. So let's write it this way. Let's say that A is the event of 2 people having the same birthday. And the complement is the event of 2 people not having the same birthday. Yeah.
It is saying that we're supposed to get rid of 3, 4, 5 people.
Yeah, I was like, I was like, yeah. So I feel like A is the event of at least 2 people having the same birthday, and A complement is the event of essentially nobody having the same birthday. So to find the probability of A, it's going to be 1 minus the probability of A complement. It's going to be 1 minus. So person 1, the birthday is whatever day it is. It's kind of weird to talk about that one. So, but let's say there's 365 days they get to pick from, right? Out of 365 days. Now, what's the probability, probability? What's the probability that the second person doesn't have the same birthday? Well, how many days of the year? We're not excluding leap years. Forget about leap years. Leap years are garbage. Unless your birthday's February 29th, then I'm sorry. So what's the probability that the second person's birthday isn't the same day as the first person's? Right, there's 364 days to choose from. So second person, there's 364 and 365 days to choose from. And then the third person, well, there's 363 days to choose from. And the fourth person, there's 362 days to choose from. And the fifth person, there's 361 days to choose from. And that's about 0.027. So there's about a 2.7% chance that in a room of 5 people, at least 2 of them will share the same birthday. Now, what's interesting about this is how many people do you need for the probability that for how many people do we need for the probability that at least 2 of I've kind of phrased this terribly. Sorry. How many people do we need for the probability that at least 2 of them have the same birthday to exceed 50%? That's terribly written. Apologies for the terrible English grammar there. How many people do we need for the probability that Jesus, sorry, that at least 2 of them share a birthday? 2 of them share a birthday exceeds 50%. Well, it's kind of hard to answer. Like doing the math is not particularly fun because you're basically asking like, when is this number going to be small enough? So we're really asking like, so probability of A is going to be 1 minus the probability of A complement. And we're essentially asking like, when is this number 365 over 365 times 364 over 365 down to kind of what number over 365 do we need to get to so that this is bigger than 0.50? I don't really want to do the math. I just kind of want to tell you because it is kind of interesting. That number is 23 people. So this number right here ends up being what? 365 minus 22 is 343. So if you have 23 people, right, just like here we had 5 people and that number was 361. This quantity, 1 minus 365 times 364 times 363, all the way down to 343, all over 365 times 365 times 365 that many times, that's going to be about what was it, 507. So it's kind of interesting, right? Because oftentimes when you ask this question, people think you need a lot more people than 23 to have a 50-50 chance of two of them having the same birthday, but it's actually quite a bit less. Kind of interesting. Kind of. All right. So where are we at? Okay. Let's continue on talking about conditional probability, which is definitely what we need to do to talk about Bayes' formula, which is certainly kind of I don't know, the thing we're working towards at this last part of the class, kind of the goal, I suppose. So let's look at some examples. So conditional probability. So these first examples are a little bit weird, but they do kind of help. So here's one. Let's say we draw 2 cards from a deck. A standard deck of 52. What is the probability that the first card is a heart and the second card is a heart? And we're going to break this down into situations. Situation A, in this situation, if the first card is replaced after drawing it. So this is often called, with replacement. So, okay, I got a deck of cards. I take one off the top. What are the odds that the first card is a heart? Well, there's 13 hearts out of 52 cards. So the probability of the first card is, I guess I can write some things down. So A is the first card is a heart. B is the second card is a heart. So the probability of A is 13 out of 52. And the probability of B is also 13 out of 52 because after you draw that card, regardless of whether or not it was a heart, put it back in the deck, and then you maybe shuffle them or whatever, and you draw another card, and same probability. So in this case, the probability of both things happening, the probability of A and B, is going to be the probability of A times the probability of B, which is going to be 13 out of 52 times 13 out of 52. Or 1 out of 4 times 1 out of 4, which is 1/16. There's a 1 out of 16 chance that if you draw a card from a deck and then put it back in and draw another card, that both of them would have been hearts. It's much more interesting and more typical with decks of cards to ask the question without replacement. And it's usually easier to think of these things without formulas, to be perfectly honest, at least at first. So what's the probability that the first card is a heart? Well, still the same, right? Still 13 out of 52. But now we've removed the card from the deck. And we want both of them to be hearts, so we're kind of assuming the first one was a heart to be able to get what we want. So after we've taken that one card out of the deck, there's only 12 cards left that are hearts out of 51 cards left in the deck. So the next probability is going to be 12 out of 51. which I don't really care what this applies to at the moment. But I want to point out what we're really calculating here is, again, the probability of A and B. And watch how this looks. It's going to be the probability of A, right? That's our 13 out of 52. The first card is a heart. But now, the second card being a heart has a condition upon it. We're asking what's the probability the second card is a heart, given that event A has already happened. We're assuming that a heart got drawn, and then we're asking what's the probability that B happened given that A has already happened. Back. Oops, come on, pens, stay together. Right, this is the probability of B happening given that A has already happened. It's really important to make sure you understand which order means which here. The thing that is written second is the thing we're assuming has happened. So it says probability of B given that A has happened. So if we know we've drawn one heart from the deck, then we know there's a 12 out of 51 chance of drawing a second heart from the deck. So this here is your probability of B given A. And then you could simplify this if you want to. This reduces down to 1/17th, I think. Yeah, 1/17th. Yeah, because 13 over 52 is 1/4, and 1/4 times 12 is 3, and 3 over 51 is 1/17. Sure. The numbers are not so important. The formula is. So, a couple things to be aware of here. The general formula for an intersection is the following. So the probability of A intersect B is the probability of A multiplied by the probability of B given that A has happened. Or the probability of B multiplied by the probability of A given that B has happened. Now, really what this tells me is the following. If I want to find the conditional probability, I'm going to divide both sides by probability of A here and say that the probability of B given A is equal to the probability of A intersect B divided by the probability of A. Or the probability of A given B is equal to the probability of A intersect B divided by the probability of B. This is the formula I think of most frequently when I'm thinking about conditional probability. Probability of B happening given that A has already happened is, well, in fact, I think it's really actually easier to see if you draw this with a picture. So if I look at this formula specifically, what I'm really thinking of picture-wise is the following. Here's your whole omega sample space, and then here you have A and B. And what you're really doing is you're saying, okay, we're saying given that A has happened, meaning we're limiting ourselves to just A. We're then asking, okay, what's the probability that B happens given that A has already happened? Well, you're essentially saying, I've got to live in the section where B is also happening. So where's my purple pen? There it is. We have to be right here. The probability that B happens, given that you already know A has happened, is the intersection divided by the probability of A. Oh, okay, that's the formula we wrote. So if we look back, I'm going to look back for a moment here at the previous example where we drew a Venn diagram. Where'd you go? Come on, Venn diagram. Just for example, right? In this example here, if I asked you, what's the probability of B given A? Well, if we assume we're living in the land where A has happened, I told you we rolled an even number. What's the probability that B happened? Well, there's only one way B can happen if we knew we rolled a 6. So the probability of B given A should be one event out of 3 possible events. So it's going to be the probability of A intersect B divided by the probability of A, which is exactly Well, the probability of A intersect B, I think it's on this page, is 1 out of 6. The probability of A is 3 out of 6. It's exactly 1/3. Which it is, right? Because again, looking at this, if you knew that a 2, a 4, or a 6 was rolled, the probability of a 6 being rolled, that B happens, is exactly 1 out of those 3 possibilities. So I would say the way I prefer to think about this as possible is to think about the given thing as kind of my new sample space. Saying, oh, look, I'm limited to just these options. And out of these options, what's the probability of getting the thing that I'm being asked about? That's often the easier way to look at it if we have the necessary information. I'm gonna put this back where it was. Sorry. Come on, pages. Cool. All right. So let's look at another example to kind of go along with this because yeah, can I fit this in here? Maybe not. Let's use a new page. So here's another example. One card is drawn from a deck of 52. Question A here. Interesting. What is the probability in the acronym for that? What is the probability it is a queen given that I told you it was a face card? And I would say there's, like I was kind of saying, there's kind of two ways to think about this. So, method one, what I would say I prefer in general, we're going to use what we typically think of as the reduced sample space. So, I told you it was a face card. So that means we know there's only 12 cards to pick from, right? There's the Jack, Queen, King of hearts, diamonds, spades, clubs. So this is what I'm going to say is oh, I forgot to name my events. Sorry, it's terrible. So let's say getting a queen is event A, and I told you it was face card is event B. We're asking what's the probability of event A happening given that B has already happened? Which I really feel like the way we say it is why you write it this way. A given B is because we really write it. We say A before B. But even though I'm really thinking of, I'm telling you B has happened and then asking you what's the probability of A. So I feel like it would make more sense if the notation was the other way, but oh well. It's not mine. I don't get to decide. So what we're thinking of is this is your reduced sample space, your sample space of just event B. And then we're asking, well, what's the probability that A happens? Well, how many ways can I get a queen? It's like 4. Out of how many cards total? It's like 12. So there's a 1 in 3 chance of getting a queen, given that I told you it was a face card. And again, that's the way I would really encourage you to try to do problems like this if you have that option. It's not always an option because sometimes they don't give you all the information you need to be able to do it that way. Like it's kind of a more like they've told you some stuff about a situation, but it's not like a set like deck of cards or a die. Like it's you have like so many people and some percentage of them have some stuff, and then doing this is kind of not really viable. The other way is to be more formulaic. So we can use the formula. Use the good old formula that the probability of A given B is exactly the probability of A intersect B divided by the probability of B. Okay, so B was getting a face card. The probability of getting a face card, and again, now you have to think about like anything could happen in the deck, right? So I pull a card from the deck of all 52 cards, and the probability of getting a face card is 12 out of 52. There's 12 face cards out of 52 total cards. Okay, A intersect B. that's getting a face card and getting a queen. Oftentimes, this will just be the one thing that's the smaller thing, right? Getting a face card and getting a queen means you got a queen. So how many queens are there? Well, there's four queens in the deck, so it's exactly 4 out of 52. But 4 out of 52 over 12 out of 52, the 52s cancel, and you get 4 out of 12, which is 1/3. Either way is fine. I like this when it works, but this is also totally good. But just remember, when you're doing it this way, you are really, your frame of reference is, oh, I'm looking at the entirety of everything and asking what these probabilities are. And then I'll remind you here, right? A intersect B, this is, in this case, a card that is a face card and a queen. Well, only queens are those cards. So that's why it's 4 out of 52. That's not always the case, but it frequently is the case where the intersection is just the one thing that's kind of the smaller set or the one that's the one that's contained in the larger one, but not always. Let's look at this next one. Yeah, we got time. Yeah, we got time. Yes. I just want to make sure I get to the thing I'm really trying to get to here, which is we're almost there. Okay, same kind of question, but now we want to find the probability of getting a heart given that we know it's a 7. And in these kind of examples, I like to imagine someone else has looked at the card and said, it's a 7. And then you're like, okay, well, there's a whatever problem. And you probably already know the answer to this question. If I told you the card's a 7, what are the chances it's a heart? 1 in 4. There's 4 different cards that are 7s, hearts, clubs, diamonds, spades, and one of those is a heart. So if I told you it's a 7, we know there's a 1 in 4 chance that it's a 7 of hearts. So again, that's kind of the method one way of doing it. Our sample space in this case, oh, and let's name, so heart is event A, getting a 7 is event B. The reduced sample space is just the 7 of hearts, the 7 of diamonds. I'm really not good at drawing these. The 7 of spades. Okay, that's not bad. And the 7 of clubs. Oh geez. The heart and the diamond are easy enough to draw. Okay, those are not the worst I've ever done. So right, that's your reduced sample space. Then the probability of getting a heart, given that it's a 7, well, there's one heart out of those 4 cards. Or you can do it the other way. Say, well, probability of getting a heart, given that it's a 7, is the probability of getting a heart and a 7 divided by the probability of getting a 7. How many cards are there that are a heart and a 7? There's one, right? The 7 of hearts is the only card that is both a heart and a 7. So this is definitely a case where A intersect B is a smaller set than A or B, right? A is all the hearts, B is all the 7s. A intersect B is just the overlap, which is the one single 7 of hearts. So there's a 1 in 52 chance of getting a 7 of hearts. Whereas the probability of B, the probability of getting a 7, well, there's 4 7s in the deck, so there's a 4 in 52 chance. And just like last time, the denominators are the same, so they cancel, and you get 1 out of 4. It's a pretty common thing that happens with these problems. Do I want to say that yet? Kind of do. Yeah. How much time? Not quite yet. No, I actually want to say. So what I want to point out here is the following. So let me ask you a different question that's related. So relatedly, what's the probability of getting a heart in a deck of cards? If I pick a random card, the probability that his heart is 13 out of 52, which is 1 out of 4. And here's what I want to point out. In this example, knowing that the card was a 7 did not change the probability of getting a heart. Knowing it was a 7, the probability of getting a heart was 1/4. Not knowing it was a 7, the probability of getting a heart was 1/4. When this is true, that means the events are independent. So in this example, events A and B are independent events. And the way I would encourage you to think about this is we know two events are independent when knowing one of them doesn't affect the probability that the other one happens. So I'm going to write that down because knowing one of them has occurred does not change the probability that the other one occurs. Or as it's written mathematically, the probability of A given B is equal to the probability of A. That shows us that events A and B are independent of each other because knowing that B has happened doesn't change the probability of A happening. And there's actually three ways of writing this. You can write it like this. You can also write it like this. Probability of B given A is equal to the probability of B. These are the ways I prefer to think about it because I think it's easier to read this and say like, oh yeah, knowing that one thing is given doesn't change the probability of the other thing happening, right? Probability of B happening is the same as probability of B happening knowing that A happened. But there is one other formulation of this, which, although I don't think the formula is as helpful because the math doesn't like just doesn't seem to make as much sense to me, maybe personally, but it is a useful formula to know. So the third way of showing that two events are independent is that the probability of A intersect B is equal to the probability of A times the probability of B. If any one of these things is true, they're all true. Because they're really all coming from the formula that, right? They're coming from the formula that the probability of, sure. There's so many ways to write this, of B given A is equal to the probability of A intersect B divided by the probability of B. Sorry, probability of A, apologies. Right, so the idea here is that this is your usual conditional probability formula, but then if the events are independent, you can replace the probability of B given A with just the probability of B. And then you can kind of see how, oh yeah, you can get that one, or you get that one, or you get that one. So when someone asks if two events are independent, that's usually how you check, is by seeing if one of these three things is true. And again, I would personally prefer the first two, but it's not always what I get to choose. Sure. So how much time have we got? Oh yeah, I got 10 minutes. Cool. By the way, I will unfortunately not be having office hours this afternoon because I have to go deal with some stuff. So, but normal office hours for the rest of the week, just not today. And then next week, all my office hours and drop in. I posted on Canvas today, but just to let you all know if you're looking for me. Let's look at one more example here. So, whatever number this is, I think it's 3. A family has 2 children. One is a girl. Find the probability that both are girls. Well, you might think the answer is 1/2. It is not, which might seem kind of weird. But it's because we were kind of cagey about how we didn't say which child is the girl. We didn't say it was the oldest or the youngest. We just said one of them is a girl. Well, let's talk about a reduced sample space. So if we say that event A is having a girl and event B is that both are girls. So let's look at our reduced sample space. It's going to be omega A. So if one of the children is a girl, well, there's three ways that can happen. You could have a girl then a boy, or a boy then a girl, or a girl then a girl. But you can't have a boy then a boy, right, which is the fourth thing that could happen generally when you're having two kids. So the probability of B given A, well, this here is what we're looking for. There's one way of getting what we want out of three things that are possible. If we have the knowledge already that one of the children is a girl. Or we can do the formula. Probability of B given A is the probability of B intersect A over the probability of A. B intersect A, one child is a girl and both children are girls. Well, that just means both children are girls, right? This is one of those cases where one of the two events is a subset of the other one. So the probability of B intersect A is going to be, well, in the whole sample space, there's four things that can happen. Girl, boy, girl, girl, or boy. So the probability of getting two girls is 1 out of 4. The probability of getting one girl, well, that's 3 out of 4. I feel like that's, yeah. So yeah, it doesn't say exactly one is a girl, right? Yeah. So it is good to think about the language here, though. Right? Event A here, where one of the children is a girl, we really should have said at least one of the kids is a girl, right? That's kind of a more correct way of saying that. But probability of A is going to be 3 out of 4. There's three ways of getting at least one girl. And again, that's 1 out of 3. Now, it is interesting if we're clearer with our language from the get-go, the probability changes. So for example, if we said different family, two children, and we said the oldest child is a girl, and then we asked to find the probability that both are girls, it's a different situation. Because now our oldest child being a girl being event A, and probably both are girls being event B, well, our reduced sample space this time is less. If we know the oldest child is a girl, there's only two things that can happen. You could have a girl first and then a boy, or a girl first and a girl. Boy girl is no longer an option because we know the oldest child is a girl. So then the probability of B given A is going to be one way of getting what we want out of two things that are possible. Or the formula, right? Probability of B given A is B and A over the probability of A. And again, to have B and A where the oldest child is a girl and both children are girls is still 1 out of 4 ways that can happen where you get girl, girl. And the probability of A happening here, well, the probability of the oldest child is a girl, there is 2 out of 4 ways that can happen. So it's a 1/2, not a 1/3 this time. So it is kind of interesting with these conditional probabilities. You have to be careful with the language sometimes. Sure. Yeah. Do you want to do that? Let's do that. Okay, one more example, and we'll call it a day. So this is kind of the lead up to what you're probably going to see at some point. Kind of a lot of words here. So a blood test for a disease shows a positive result in 98% of the cases when the disease is actually present. Okay, let's pause for a second. There's more to write here, but I want to say that here. So what that's telling me is, given that someone has the disease, the probability of a positive test is 98%. So if we say that D is the event of having the disease, and plus is the event of a positive test, then the probability of a positive test, given that someone has the disease, is 98% or 0.98. Sorry, there's more words here, comma, and in 6% of the cases when the disease is not present, meaning a false positive. So that would mean we're saying that the probability of a positive test given that someone doesn't have the disease, right, the complement of that is 6%. Assume the prevalence of the disease is 1 out of 250 people. So the probability of having the disease is 1 out of 250, or 0.004. Right? 1 out of 25 is 4%, so 1 out of 250 is 0.4%. All right, so question A. If we select someone at random, we select a random person, what's the probability they have the disease? No, that we are not. So that question I was about to say, we already know the answer to. It's 1 in 250. What's the probability that they test positive? Well, there's a couple ways to think about this. Here's what I like. I like to make a tree diagram. Specifically for these questions, I think a tree diagram is really helpful. So you've kind of got your branches of your tree, where the first branch, your person either has the disease or not. And usually when you're doing these branches, if it's possible, you kind of want to look at your conditional probabilities up here, say, okay, I would like my first branch of my tree to be the branch of the thing that's given in my conditional probabilities. So my first branch, either the person has the disease or they don't. And in my next branch, the person either tests positive given that they have the disease, or they test negative given that they have the disease. Or over here, they test positive given that they have the disease, that they don't have the disease, or negative given that they don't have the disease. And we know all these probabilities. Probability of having the disease is 1 out of 250. Probability of not having it is 249 out of 250. The probability of a positive test given that we have the disease is 0.98. Probability of a negative test given that we have the disease is the leftovers, 2% or 0.02. Probability of having a positive test given that we don't have the disease or a false positive was 6% or 0.06. So the probability of a negative test given that we don't have the disease is the rest, 94%. And then the probability of a positive test is all of the pathways that get us to a positive test, meaning this times this, right? Having the disease and having a positive test. So we multiply. Or we add not having the disease and having a positive test. 249 out of 250 times 0.06. This is approximately, I forget what it is about. It ends up being approximately 0.0638. So the probability that the random person on the street would have a positive test is about a little more than 6%. Now, what's kind of interesting is most of those are probably false positives, right? Because, right, that's mostly coming from here. What this is also showing us, that this, I know we're out of time, but let me say one more thing here real quick. This probability of having a positive test is really the probability of having a positive test and the disease, or a positive test and not having the disease. Right? Those are the only options. If you test positive, you either have the disease or you don't. So this is called here the law of total probability, where you're trying to find the probability of something happening. You break it up into that thing and whatever the other kind of situations are, and disease or and not disease. We'll talk more about this on Thursday. We'll talk about, we're almost there talking about Bayes' formula, which is going to help us answer the question, what's the probability that I have the disease given that I tested positive? Which is what you actually want to know, right? I don't care about if the test is, is positive 98% of the time someone has the disease. You already know you have the disease, you don't need the test. But if I test positive, what is the probability that I actually have this disease? That's what I really want to know. All right. See you all next time.